Okay, we are starting with the very first lecture now for this course, which is analysis of functions of single variable and ODEs. So the very first unit we are going to learn here is real number systems, where we will learn some very important properties of real numbers. And then we will look for convergence of sequences and summation of infinite series. Okay, and then we will move to the next topic, which is directly related with the function of single variables. And these definitions are well known intermediate people as well, that they are very well aware about limit, continuity, and differentiability definition for a function of single variable. So we try to get some depth knowledge about it and try to relate them with the real life problems. Okay, and look at these problems also spatially. Okay, so this will be first unit, so that we are going to start. The textbooks and these reference books are available in your resource section in a library. You can ask for the access of these books. Okay, those are available with your library. Okay, right. It's already I have posted, so that information only here. Sure. Okay. So the very first thing I wish to go with is some brief survey on sets. So if you recall, what is a set? A set is a collection of well-defined objects. Okay, a collection of well-defined objects means that objects have some meaning, like set of integers, set of rational numbers, and set of irrational numbers, set of real numbers, or you can say that the collection of objects which are defined by some relations. Okay, but can you give me an example of a collection which you cannot specify as a set? So by the definition, it is clear that a collection of well-defined objects. So can you give me an example of a collection which is a collection of elements, but they are not well defined?
Best batsmen in the world.
Yeah, great. So best batsman in the world. So those things are like prediction you have. Yeah, good students. Okay, right. So many examples are there. So where you can see these cannot be defined as a set. So next we are going to have one when you will say an element is inside A or outside A. So this is a mathematical notation for belongs to. Okay, that's reverse epsilon. Okay, that so X belongs to A means X is an element of A. And otherwise, if it is not there, so we just cross it, means say that X does not belongs to A. Okay, so these things, this is you are aware. Okay, so if every element of a set A is in a set B, we say that A is a subset of B or B is a superset of A. So I hope there is no difficulty in understanding this. When you say A is a subset of B or B is a superset of A. And when you will say A is equals to B, two sets are equal when A is a subset of B as well as B is a subset of B. So that also is clear. And we say that A is a proper subset of B if you are able to find an element in B which is not an element of A. So that you will say is a proper subset of B. Okay, right. Now we say that A is equals to B if A is a subset of B or B is a subset of A. Now, so let's have very first example, the set of natural numbers as set, the set of integers positive integers, negative integers, set of rational numbers. So rational numbers we are writing in the form of m by n, and where m and n are in z, and any, of course, denominator should not be 0. So that's how the set of rational numbers are defined. And then the set of real numbers. So it's a means which is a set of rational numbers union with set of irrational numbers, which is not rational. That's what it is. So we will come over it again. The set, the very good set is here is the set of all natural numbers which satisfies this equation. It's also forming set. So you have this x minus 1 into x minus 2 equals to 0, 0, 1, comma 2, the root of this equation. Okay, right. Now set operations, like A and B are two sets, then you define their union as a collection of all possible points in A and in B. So, okay, means as well as means it's not, I cannot use and here. Okay, that is specific for intersection. So A union B means you have collect all the elements in A from A, and also collect all the elements from B, and then you write in the form of set. So in a set, the items cannot be repeated. You recall. Okay, in the sequence, if you write in the without the bracket, they can be repeated 0, 1, 1, 2, 2, 2, and so on. But if you write in the set, they only occur in once. So A union B, a collection of elements X such that either X in A or X in B. Okay. So an intersection, how will you write this? An element X, collection of X such that X belongs to both A and B. Okay. With the finite thing, no problems. Okay. Many problems are not there. You can perform integration, derivative, and many things are very good with the finite things. Right. So we will come to that. So the complement of B related to A. So that's how we will pronounce. A minus B is the complement of B relative to A is the set A minus B is equals to the collection of X such that X in A but not in B. So we are just going to delete the items from the set A which are also in B. Okay. So that will be A minus B. Okay, right. Now the set, okay, then we have this convention phi, the notation you can say. The notation phi is the notation for empty set, means a set which does not have any element. So this empty set is always a subset of every set. Okay, right. Spy convention. Okay. Now, if A, B, C are three sets, then these following distributive law. Okay, so this is a distributive law, right? Or in other words, it's also known as De Morgan's law. A minus B union C is equals to this. So this can be understood by using a Venn diagram. So this is a universal set here. Let's say U, and you have A, you have B, and you have C. Okay, so this is A, B, and C. So what is A minus B union C? So B union C is, if you recall this B union C. So this is your A minus B union C. So now if you look, A minus B will give you, will be A minus B is what? This is the A minus. And A minus C is what? This is the A minus C. So if you make the intersection, it will be A minus B, and A minus C is nothing but A minus B. Similarly, you can show for A minus B and C. Okay, that is very simple to prove. And now we can prove it mathematically as well. X belongs to there, then X belongs to both, and so on. Okay, right. Now, if you have an infinite collection of sets, then how will you define their union? How will you define their intersections, and so on? Okay, So we'll see that. So their union is nothing but the set of elements that belongs to at least one of the set A. So earlier A union B was X is in X such that X belongs to A or X belongs to B. Now, if you have a collection of infinite sets, so if you want to write the notation for union I is equals to 1 to n AI. A1 union, A2 union, A3 union, and so on. So it collects all, this is a 1 to infinity. It's an infinite connection. Okay, now this their union is nothing but a set of elements that belongs to at least. So if one of the AI contains X, that will go into this. And their intersection is what? The set of elements that belongs to all of these sets A. Okay, right. So you can take like a set of natural numbers. Okay, and that can be written as union I is equals to 1 to infinity singleton I. So each AI you can define as you have this is AI is equals to singleton I. I is equals to 1, 2, 3, 4, and so on n. So set of natural numbers can be written as an infinite union of this singleton sets. Now, if you recall, if you find out that their intersection is going to be an empty set. Their intersection is nothing but the set of elements that belongs to all of these sets. So this their intersection, if you want to get it, that's nothing but the finite that empty set. Okay, right. So this is how you will deal with intersection, infinite intersection. How will you write it? Instead of this, this cup, you have the cap. I is equals to 1 to infinity AI. That belongs to all of these sets. Okay, so if you take the intersection of the following example, it will be an empty set. Okay, now we are in the position of defining the functions by using the definition of now sets. So if A and B are non-empty sets, so that's important, A and B are non-empty sets, then their Cartesian product, how will you define is A cross B? So if I write in notation A cross B is equals to set of all ordered pairs such that first entry belongs to A and second entry belongs to B. So this will define the Cartesian product, and this will again form a set. Okay, this is going to form a set. So if you want to look at example of real life examples, or means you can say if you want to connect it with the real line, so you can talk about the plane R cross R. Okay, so you have XY axis now. So R cross R can be identified by the plane. Okay, so if you try to identify the Cartesian product. So if you once more multiply R cross R, you will get space. Okay, and so on, 3-dimensional, 4-dimensional, and so on. Okay, so that's a direct connection between real line and this Cartesian product. Okay, now how will you use this to define the definition of function is as follows. So you are going to define a function as a pair. First entry is, I mean, like you are going to define a function is from F from A to B, set A to B. Now, when you are defining a function on a set, it should be well defined. Means it should be defined on each and every element of A. Means for every element, if you take X belongs to A, F of X must be defined. So by default, so what this A is called domain of F. Okay, and if you collect all the set points F of X such that X belongs to A, that is called the range of F. Okay, so range of F may or may not be equals to B. It will be what we know is going to be a subset of. Okay, so how this function is going to be a subset of A cross B means like you have A comma f of A. How it is be identified for each A belongs to A, this pair will identify the function. Okay, or you can say graph. Okay, this is a graph A comma f of A. So you can get for each point you can plot on the xy plane, you will get a curve, and you will get the function definition. In geometrically, you will get a graph of it. Okay, right. So let A and B be sets, then a function say f from A to B is a set of ordered pairs in A cross B. For each A, there exists unique element B in B with AB belongs to F. So how will you define this B is as f of A? Okay, so this is what the definition of function. So if you collect, so that's what I mentioned just now, what is a D of F, domain of F, and what is, so that we are going to identify, define now. Okay, so the set A of first elements in F. So if you here, F is can be identified by, and you can have this F is can be identified by A cross B, or you have this A comma B, such that B is equals to F of A. That's how to define it. Okay, so the set A of first elements in F is called the domain of F. We denote it by D of F. Okay, so we denote it by D of F. The set of all second elements in F is called the range of F. We denote it by R of F. So again, I wish to specifically tell you that's going to be collection of all X such that X belongs to A. Okay, right. So now you can talk about what is the meaning of direct image or inverse image and so on. So let's see these things also. Let F from A to B be a function with domain definition is df is A and Rf is a subset of B. We are not saying it's a proper subset, or it's not. We are also not saying it's never equals to B. So it may be equals to B, but it may be a proper subset of B. Rf. Okay. So now, when you're talking about the image, direct image of E under F, means you are talking about F of E. Means we are talking about the image of E under F, means you are talking about a subset of A. Okay, and then how you are defining this as you collect all the elements in A from E and you take the image of them and you make it set that we'll call as the direct image of E under F. So when you talk about direct image, means you are talking about the image of subset of A. When you're talking about inverse image, means you are going in a, so previously you are going in the forward direction, now you are going in the backward direction. So from B to your, so F of E is now is a subset of B. Now here F inverse of H is a subset of A. So if H is a subset of B, then the inverse image of H under F is the subset of A is given by this. Okay, so this is how you will define the direct image and inverse image of subset of A or subset of B under F. Okay, that will be useful for defining the equivalence relation of continuous functions and all. Okay, that we will see. We'll relate it later with the continuity of functions as well. Right. Now the next is a special type of function, means when you will say injective, or when you will say surjective, or when you will say bisective, or when you say it has an inverse, and so on. So let F be a function. So we say that F is injective or 1, 1 if you take two distinct elements, their images will also be distinct. Or if you take if you assume that f of x1 equals to f of x2, then show that x1 also equals to x2. That's the way of showing that the function is injection or injective or one-to-one. Okay, we say that f is surjective or onto if you have the range of f, you can say, is equals to b, or image of the set A under f is actually equals to b. Okay, means you take any element in B, you always able to find an unique A in A such that f of A is equals to B. This is what it means, the surjective or surjection. So if it is injective and surjective both, we will say that this is bijective. And then you can talk about the inverse. Okay, right. So we say that it's bijective if f is both injective and surjective. So note that f from A to B, if it is injective, you can make it surjective. If it is surjective, you can also make it injective by restricting a function. Okay, so if suppose function is injective, then you can make that f from A to, instead of B, you can take R of f. So this will be a bijective map now. If f is injective already, then it is a bijective. Okay, so let's have that, and let's have an example now. So let A is a set, x belongs to R such that x not equals to 1. And define f of x equals to the for all x in A. So now first of the thing is you need to see whether function is defined or not on A. So A is the set of all elements, set of real numbers, such that x is not equals to 1. Now you can see that f of x is defined everywhere except at the point x equals to 1. But you have taken one is outside the A. So it is well defined on A. So domain is fine. Now you have to show that f is injective and find the range of f. So let's do this problem. So what is given is the A is the set x belongs to R such that x not equals to 1, and the function definition is f of x equals to 2x by x minus 1. Now you have to show that claim is f is injective or one-to-one. So let x1 comma x2 belongs to A such that f of x1 equals to f of x2. Then if you show that x1 is equals to x2, then you are done. So this implies by definition 2x1 by x1 minus 1 is equals to 2x2 by x2 minus 1. So this will implies 2x1 x2 minus 2x1 is equals to 2x1 x2 minus 2x2 cross multiplication. So this will get cancelled. This implies x1 equals to x2. So it implies f is 1. Now, what is the next problem here is find the range of f. Now, if you talk about the range of this, range also is subset of real numbers. Okay, so again, if you input give you real number, output also a real number. So what is range of f is equals to f of x such that x belongs to A. So let phi belongs to Rf. So that is, this implies there exists an x in A such that f of x equals to y. So this implies 2x by x minus 1 is equals to y. This implies, so you solve it back for x now. So 2x is equals to x into y minus y. So this implies x times y minus 2 is equals to y. This implies x equals to y upon y minus 2. So the range is well defined for every y except for y equals to 2. So range of f is what? I must say that is going to be x belongs to R such that x does not equals to 2. Or you can say y belongs to R such that y is not equals to 2. So for any y, now it is defined except at 2. So this will be the range of the given function.
So x not equal to 1, so y cannot be also equal to minus 1.
No, range of f, see, y can be equals to 1. We are talking about range, right? We are not talking about domain. So in domain, x is not equals to 1. But in range, x may be equals to 1. So you will have, right?
Yes, sir.
F of x image could be value equals to 1. So if you image you take 1, for which value? So that is going to be
minus 1.
okay, yeah. When x equals to minus 1, it's going to be minus 2 divided by minus 2. That is what y equals to 1, right? So 1 may or may not, 1 is also a member of range of f, but it is not a member of domain of f. So we are very specific for now, range of the set f. Okay, right. Let's go further now. So now let's talk about inverse function. If f from a to b is a bijection of a onto b, then you have the ordered pair a cross b earlier, now it is a b cross a. Then bg, which is identified by b comma a, such that a comma b belongs to f. So that will be is a function on b into a. This function is called the inverse function and is denoted by f inverse. So now let's work with the same example now. So we have already shown that it is injective. We have also found the range of f. So we are now in the position of writing its inverse. So if you go back and check again, you have domain of f is a, which is r minus 1. And range of f is r minus 2. We have already shown that it is a injection over the set A. So f from A to R of f is a bijective. Is a bijection. Its inverse, f inverse from f to A is given f inverse of y is equals to y divided by y minus 2. Just now we have derived. In the same way, we are going to derive the inverse image of this. Okay, so the inverse of the function is identified here for this particular. Okay, right. Now let's talk about when you will say a set is finite, infinite, or countable or uncountable. Okay. Now, so very first we should talk about the empty set. So convention, so there is no point. So we say that this has set to have 0 elements. Okay, there is no element. So we say that there are no zero. There are no elements. So the cardinality or number of elements that we are going to define by this, by putting this mod on the both sides, that is going to be 0. Okay, so that we are going to take. Now, if n belongs to n, then we set as is said to have n elements if there exists a bijection from nn onto x. So if you define f from s to nn, So you can define S equals to A1 to AN. Now you can define f of AI is equals to I, or f of I is equals to AI for I equals to 1 to N. So this will give you the bijection from NN on to S. Why we have considered in this manner is because it will directly, now we can generalize to countable. Okay, right. So NN is nothing but the subset, finite subset of set of natural number, which is consisting of N. If you are letting N tends to infinity, that finite will becomes an infinite set, but still it is countable. Yes, you have 1, 2, 3, 4, 5, 6, 7, 8, and so on. So this will tell you the countability. If you are not able to do so, means you are going to have the uncountable. Okay, right. So if a set S is said to have n elements if you are able to find a bijection from Nn onto S, and which is okay, that you can, this is a bijection. Whether you talk about S onto Nn or Nn onto S, both are the same thing. Okay, right. Now a set S is said to be finite if it is either empty or it has n elements for some n in n natural number. Okay, a set S is said to be finite if it is either empty or it has n elements for some n belongs to natural number. Okay, right. And we say that this cardinality of S is means either 0 or n. If it is empty, it is 0, or it has n elements, means that n. Okay, right. A set S is said to be infinite if it is not finite, which is neither empty or nor it has n elements. Both things are not. So then you will say, or in other words, you are not able to fix small n such that you are not able to means so that you are not able to find a bijection from Nn onto S. Okay, for every n, that's what it now it means, like there is no bijection, okay, such that this happens for every k belongs to natural number. There is no bijection. Then you will say that S is said to be infinite. Now you have a denominable or countably infinite if there exists a bijection from n onto S. So that's what I was telling you, that if you are letting n tends to infinity, that tends to Nn tends to n. Okay, then if you are able to find a bijection from the set of natural number onto S, set is said to be countably infinite. Okay, or then if it is not possible, then we will say that it is the set. Okay. Said to be countable if it is either finite or countably infinite, or you say in other words denominable. Otherwise, you say that S is uncountable. So to show that a set is countable, you need to prove mean either it is finite, means you have to show that there is a bijection from Nn onto S, or you have to show that it is countably infinite, means there is a bijection from N onto S. If nothing is possible, neither this or nor this, means then you have said you can prove that S is uncountable. Okay, so let's very first example, the set of natural number is countably infinite. So it's very much you can prove that that is not finite. Okay, because this function f from nk to n is not a bijection map, because you will have a k plus 1 for which you don't have any entry here in this. Okay, right. So there is no such bijection for fixed k. Okay, so it is not finite. Now f from n to n, you need to show that this is a bijection. Means there is a bijection, means you are able to find a map. Okay, not it is not the map. Okay, so For this example, for this problem, the bijection is very simple. You can go with the identity function. F of I is equals to I. And you know that identity function is bijection, right? Both 1, 1 and onto both. And so this is a bijection from n onto n, and this guarantees that now n is countable. Okay, so this is a very simple example for looking at the countability of set of natural numbers. Now, the very next is the set. If you take Cartesian product of n with itself, that is also countable. Okay, so before going there, so let me show that the set Z of all integers is, the set Z of all integers is countable. So the important thing is to find a bijection. So we are going to first solve this problem of 3. Okay, means we are able to show that there is a bijection from Z onto N, or N onto Z. Okay, so we are going to take map, we are going to define a map F from N onto Z as follows. So what we are going to define is F of 1 to be 0. Now, and then F of 2, the positive 1, F of 3 to be negative 1, F of 4 to be positive 2, F of 5 to be negative 2, and so on. So what it says is F of 1 is 0. So for 0, you have a unique one now. Okay, now here, see, for even natural numbers, you are mapping with the positive integers. Odd natural numbers, you are mapping with the negative integers. Okay, and you can prove that this is going to be 1, 1 on 2. Okay, so that is very simple, right? So if you take any set integer k, okay, so if it is k is greater than equals to 0, greater than 0, if k is 0, that is 1, f of 1. Now k is greater than 0, then you have, and suppose then k is greater than 0, then it is the image of f of 2k. If k is less than 0, it is the image of f of 2k plus 1. Minus minus plus, so 2k plus 1. So that is going to be k minus with minus sign. So you have a uniqueness as well as injections, or as well as one-to-one property as well. Okay, so this way you can define the bijection of from n onto z. Okay, right. Now let's identify the bijection from n cross n onto. Now we are going to show that example 2 that n cross n is countable. Yeah, a question?
Sir, it would be like f of 2k plus 1 is equal to minus k, no? In previous example for negative.
No, k is negative already, right? See, when you are taking the image, means the map, this is a positive number only. When you have k is negative, so k is a negative number. So minus 2, minus 3, minus 4, minus 5. So you have to make it positive to put it here. So you have to multiply by minus.
Minus plus. Yeah, okay.
Okay? Right.
Yes. Yes.
Okay. Now, n cross n is also counted. So that we are going to show now. So we have to define a map which should be bijection from n cross n onto n. So what you can do is, here is the way. We are having the following diagonal structure now. we are going to ordering the pairs n cross n as follows. So 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, and so on. And now here 1 comma 2. Here is 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4, and so on. Okay. Similarly 3 comma 1, 3 comma 2, 3 comma 3, 3 comma 4, and so on. 3 comma 5. This is going to be and so on. And we are going to now go with the counting principle now diagonally. So you have one diagonal, second diagonal, third diagonal, fourth diagonal, fifth diagonal, and so on. So it is going to be defined as, so now in the first diagonal entries are 1, second diagonal entries are 2, third diagonal entry is 3, fourth diagonal entry is 4, and so on. Okay, so this is this structure. In this structure we are talking about n cross n. Okay, so what is the sum of means in the kth diagonal? So if I take this C psi is a counting one, that is going to be at the kth diagonal. So fourth diagonal, what 1 plus 2 plus 3 plus 4. So that is going to be 1 plus 2 plus and so on plus k. So that is going to be k into k plus 1 by 2. Sum of k natural number. So number of entries in the diagonals now. Total number of elements in first k diagonals. So k diagonals. Now we are going to define a function h from n cross n onto n as follows. So you are going to take any pair m comma n. So how will you identify m comma n? Means we are going to find m comma n somewhere here in the structure. So how will you reach that? So m comma n, sum of these two m plus n. Now kth diagonal, if you see, first diagonal has the sum is 2, second diagonal has the sum is 3, third diagonal has the sum is 4, fourth diagonal has the sum is 5. Okay, now see the first diagonal, if you take the sum of elements, means in the pair 1 plus 1 is 2. If you take all the pairs here, sum is 3 in the second diagonal. In the third diagonal, sum is here is 4, 5. So where this m comma n will be placed? The sum is m plus n. So it will be placed in the diagonal where the entries has the sum as m plus n minus 1. Right? Now go below with it. So with one more, because m comma n will be one of the entry. M comma n will be one of the entry. The sum of this diagonal is going to be m plus n minus 1. So here m comma n will be one of the entry. So this is going to be psi of m plus n minus 2. Means first previous diagonal has the sum is m plus n minus 1 minus 1. That is m plus n minus 2. Now once you have covered this, now you are going into this row, actual row where m comma n is lies. So where this m will place 1, 2, 3, 4. If you start from here, it will add with the mth number. So look at here. So 1 comma 1. Where so suppose I want to find the place of 2 comma 3. So where it is here is first this column, this diagonal, and this diagonal. Now here is the third diagonal 1, 2. Second. because m is 2. If m is 3, it is third one. So this is going to be defined as plus m. So at mth place in the diagonal entry, if you look there, okay, it's going to be at mth place. Right? So this will be the definition of this function which we are going to show the bijection. Okay? Right. So here we are close today. Okay. So you have any question?
Yes, sir. Can you explain again how -2 came?
-2.
M plus n minus 2.
Because the sum of the m comma n pair is m plus n, which lies in the diagonal is where which is having thus means which is the here suppose you are looking at m plus n is means 4. Okay, m plus n is 4.
Yeah.
Okay, so if you look at the fourth diagonal, the sum is 5.
Yeah.
Right, but you're looking at the diagonal where sum is 4, so 4 minus 1. So similarly, m plus n minus 1th diagonal will contain this element m comma n.
Oh, okay.
Okay, and now because you have to count till m comma n only, so for finish till this counting m plus n minus 2 diagonals, that can be given by the summation of 1 plus 2 plus and so on plus n plus n minus 2. Then you start with in the next diagonal from the left and go downward and count it till m. Okay, so that will be plus m. So that will give you the definition of this function h. Okay, then now the next we are going to show in the next lecture that this is going to be give you a bijection map.
Sir, he is asking that what we have to find in this question. What we have to find.
In this question, we have to find a bijection from n cross n onto n, so that we can show that n cross n is a countable set.
Sir, so
If you
how
go
could
to
we get to know which specific function we have to take for bijection?
Yeah, that's a tricky question. So this cannot be answered, right? It is going to be this problem also itself is a result of a research. So I can't tell you that the specific function is you are going to get by this specific rule. It is not possible to specify that. So at present at this stage is where you don't have any method or any rules to identify a function. So this cannot be answered here. So this
So
itself is a result
it,
of
right?
too much research.
So for now, we have to remember it.
Yeah, for this problem, you have to remember it. There are other ways as well, means, but this is the simplest way. This is the simplest function you can say. You can look for search also, and there you can also see that when this n cross n is said to be countable, and there you will find number of pages for the proof as well for a particular problem. So this is the simplest proof you have.
Sir, sir, in this question, what we are trying to find means you made diagonals means the number of elements, or what means what we are trying to find?
We are trying to so finally we are trying to identify the position of the point m comma n in this diagonal structure.
Okay, position.
Yeah, position. At what point means if you are starting from the lower point, lower diagonal, m comma n is placed at which number? It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What will be the actual number of or actual place?
So by this, how we can find that it is bijective?
Yeah, that's what that will be answered in the tomorrow's morning session. This will be bijection because see, place is unique. It's an identification. So uniqueness will give you the feeling that it's going to be a bijection. It's going to give you feeling, intuition. Okay, it's not proving. It requires a mathematical proof too, but it gives you intuition that it's going to be a bijection. Because every element, if you place in a some you can say some particular specific fashion, so like this fashion we have done, so at what place it is there, it is going to be that place is going to be unique, because on that place you will not find other element placed. So that is a uniqueness.
Every element has a unique position. That's why.
Yes. Okay, so that gives you the intuition that this is going to be bijection. Now, the mathematics ground should be there so to prove it.